Hello everyone, my name is Sukanta Bose and I'm from the Inter-University Center for Astronomy and Astrophysics, IUCAA. I'll be giving a set of lectures on general relativity, 5 in all, and these will be the topics that I'll try to cover. Today I'm going to give some introduction to tensor calculus. I'll motivate it with some examples from electrodynamics as to why tensors can be useful mathematical construct in the context of understanding gravity. And then in the second lecture, you will come to the realization that gravity is but space-time curvature. So how do we define curvature? In this case, in terms of tensors is what we're going to learn about there. The third lecture will be on a special type of tensor, namely the stress energy momentum tensor, which you may have encountered even in special relativity or electrodynamics. And then we will introduce the Einstein's equations that relate the stress tensor, for short, of any fluid distribution, physical of course, to space-time curvature, which in turn is given by or described by another type of tensor called the curvature tensor, the Einstein curvature tensor. In the fourth lecture, we will solve Einstein's equations of gravity. First, in the case of no fluid distribution, so in other words in vacuum, and then we'll introduce some symmetries, specifically spherical symmetry, and without any time variation. So that is when we will obtain the Schwarzschild solution to Einstein's equations. And the Schwarzschild solution describes the space-time around stars, okay, so outside of stars, or black holes that are spherically symmetric. So black holes will be discussed as well as a special case. And then in the final lecture, we will bring in matter and solve Einstein's equations in the presence of matter. Specifically, we will talk about another compact object, not as compact as a black hole, but something very close to it, and these are known as neutron stars. They are neutron-rich matter, possibly the densest form of matter before it collapses into a black hole. That is, if you give it a strong enough perturbation or dump more matter into it, and the object is unable to withstand that extra matter with whatever resources it has to prevent it from collapsing under its own weight. What you see here in this panel to your right is a simulation produced by numerical relativists. I mean, these are colleagues from the simulations of extreme space-time, so SXS collaboration of multiple institutions around the world. What they did was to produce or to solve Einstein's equations of gravity to mimic the orbit of two black holes around each other, but as they went around this motion, they lost their gravitational energy in the form of gravitational waves, which in turn got their orbit to shrink, and eventually the only thing they could do was to collide with each other. So this snapshot is just before that collision and the formation of a common black hole, the daughter black hole, which will be more massive than the two parent black holes. This is a simulation of an event that made news a couple of, well, it made news a little over 2 years ago in 2016, but it was observed by LIGO and Virgo collaboration scientists in September 2015. So with that plan for this lecture schedule, let's actually begin with some notation and convention. So in much of the lectures, I'm going to set the Newton's universal gravitational constant g to 1, and I'll do the same thing for the speed of light in vacuum. So c will also be set equal to 1. There will be places where I will bring them on, especially when the dimensions of the quantities and the units are important. For example, if you want to make measurement of some quantity, such as the density inside a neutron star. And then for indices on vectors and tensors, we will use Greek letters to denote all space-time indices. Roman letters like I, J, K will be reserved for spatial indices only. So, x, y, and z components of vectors or tensors. The time index will be denoted by t or z. By the way, I'll also use numbers like 1, 2, 3 to denote space indices. So, 1 in this case will mean the x component, 2 the y component, and 3, you guessed it, the z component. Newtonian gravity, of course, held sway for some centuries before certain inconsistencies started creeping up between its predictions and observations, right? But it is still useful in launching rockets and in planning the orbits of satellites going around, for example, the Earth. It was very successful in explaining Kepler's 3 laws of planetary motion. So, what does Newtonian gravity tell us? It tells us that the force between two objects, let's say masses 1 and 2, it's a vector quantity. In magnitude, it is proportional to the product of the two masses, m1 and m2, but inversely proportional to the square of the distance between them. The proportionality factor here is Newton's gravitational constant g, which here I have written explicitly, and its value in SI units is about 6.674 times 10 to the minus 11. This force is a vector, so the attractive gravitational force, so gravitational force is attractive in nature, and that attractive force directed towards m2 on m1 is going to point from m1 towards m2. Okay, so that is what the direction of this force will be. But in spite of the success, the one problem with Newtonian gravity is that signals in this theory propagate instantaneously from any point to any other point in the future, and gravitational waves do not exist. And that is inconsistent with special relativity, where we know that if the sun were to disappear suddenly from the solar system, so suddenly you just have vacuum at the center, at the barycenter, near the barycenter of the solar system, then Newtonian gravity would have us believe that we will feel that absence instantaneously. But special relativity tells us that any such information or signal can at best travel at the speed of light, and in this case speed of light in vacuum, because the space pervading between the sun and Earth is mostly vacuum. So it will take about 8 minutes for Earth or Earthlings to realize that the sun exists no more, right? So the Earth has to respond, the Earth's future motion has to respond to that absence, but it can't happen instantaneously. The signals should propagate in some form. In this case, like in gravitational waves, of course, the sun also emits light, so that's another way to verify if the sun still exists 8 minutes later. But Newtonian gravity does not entertain that upper limit on the speed of information or the existence of gravitational waves. So those are problems, but that is not how the first realization of a problem actually cropped up. This happened in very accurate observations that astronomers had already made in the 1800s of Mercurius orbit. Okay, so this is the planet that is closest to the sun, and what you're seeing here is an animation that is quite a bit exaggerated of the fact that Mercurius orbit is not a closed ellipse, contrary to what Kepler's first law would have us believe. Okay, so rather it is a precessing ellipse, and it is the speed of that precession that is exaggerated. And regardless, the point is made clear here, namely that this precession actually was observed, and most of this precession, it turned out, can be accounted for due to the pulls and tugs by other objects, basically planets in our solar system, except for about 43 arc seconds of that precession per century. That, you know, in spite of a lot of attempts, including a suggestion for modifying that inverse square law for the force of gravity that you just saw in a slide or two ago, all of those attempts failed to explain this discrepancy. And that's when eventually, you know, there were stalwarts like Poincaré and Lorentz and finally Einstein, who realized that maybe the explanation for this lies via special relativity, but ultimately in a modified understanding of what gravity is, namely that gravity is not a force, but it is space-time curvature. So if you have a dollop of mass, in this case in the form of the sun, then the presence of that mass or inertia curves the space-time around it, which can be tracked by moving objects, you know, masses or even photons or particles of light. So you imagine, you know, in the absence of sun, so just imagine you're playing God and take away sun from here, you could crisscross this spatial volume with grid of laser beams, right? So this will set up a Cartesian coordinate system, three-dimensional Cartesian coordinate system for you. For the moment, we are ignoring time, the time coordinate. But if you suddenly bring in this mass in the form of the sun into this region of interest, that presence will warp these laser beams or their paths. Okay, so these laser beams are still trying to travel the shortest distance between any 2 points, some, you know, starting point away from the sun and some other point behind the sun. But these straightest possible paths also, which turn out to be the shortest ones, actually will become warped. And that warpage is an indication or even a measure of the curvature caused due to the presence of the sun. The presence of the sun in the form of an equation can be described by the stress energy tensor T mu nu. This is something we'll talk at length later in these lectures. And how much this, by the way, a component of T mu nu that you could have guessed is the energy density of the sun, which you would suspect has some bearing on how much the sun is able to curve the space-time around it. But it has other components like if you were in the sun, inside the sun, then also the space-time will be curved there. So it is affected by the energy density of the sun, but also by the pressure exerted by the fluid in the sun. And then there are other components which we will expatiate later. So that stress energy momentum tensor creates curvature, and curvature can be measured in various ways, and we will again describe that in detail. But for the moment, it suffices to remember that gravity is governed by a relation between the stress energy momentum tensor of the fluid here and the space-time curvature described by what is known as the Einstein curvature tensor. So G mu nu here, the G mu nu here is Einstein's curvature tensor. Now, you know, in a scientific method, it is not enough to propose a theory and a set of related equations to explain an observed phenomenon. In this case, it turns out that this equation does tell us why Mercury's orbit should precess. Okay? And it in fact tells you exactly by how much it will precess, and that extent is determined by how far Mercury is and by the mass of the sun, which is pulling on Mercury. In a scientific method, the additional thing that is required is to use your theory and equations to predict new phenomenon to be observed later. I mean, if you are not able to observe such phenomena, eventually you may have to reject your theory or give up on your theory, right? But it's really nice if you're able to test those predictions with observations, and if the predictions differ from the observations, then again that's a weakness of your theory. But if new observations verify your new predictions, then that completes this circle in the scientific method. Okay, that is when your proposal becomes, or your hypothesis becomes, a theory. So in this case, what Einstein predicted is the following. He said that the same equations also tell us that light should bend in the vicinity of any massive object, because after all, light is, as I mentioned, in the form of those laser beams, they're trying to travel as straight as possible, but in this not so flat geometry around the sun. So light from faraway stars should also bend. Of course, we are talking about stars. In this case, we want to view them, and they have to be on the other side of the sun, so very remote. But how do you observe these stars or the bending of their light in the presence of the sun? So this was predicted in 1915, 1916. It was observed finally in 1919 by Arthur Eddington and a team of astronomers working with him. And it's not just the bending, but also the amount of bending was exactly as Einstein's theory of gravity, namely general relativity or general theory of relativity, predicted. And it happens for the sun to be 1.75 arc seconds of deflection. Okay, so you because of this bending, so you the observer are here. Because of this bending, it appears to you that the star actually is positioned there, but you wait long enough, and then you view these stars again when the sun has, well, the sun doesn't really move away, but you move around the sun, and you again can measure separation, the angular separation between different stars, remote stars, and you verify that yes, if sun is in the way, then it does cause that bending, okay, relative to when it is not in the way. There are multiple other predictions that Einstein's gravity or general relativity has made, and they have all passed these test observations with flying colors. I'm not going to have the time to discuss all of them, but some of my colleagues will actually bring up some of them. And one of these predictions is gravitational waves, which will be discussed by one other colleague. So I'll prepare the formalism for you that can be used or assumed by these other lecturers. We will, so yeah, gravitational waves, yeah, they were predicted in around 1917 by Einstein, and they were observed. Actually, their presence was known indirectly as early as 1978 by tracking the motion of a pulsar around another neutron star. This was a binary pulsar system termed as the Hulson-Taylor system, described or named after the two discoverers who were given the Nobel Prize in 1993 for that discovery, and also for showing that these two compact objects, neutron stars, were actually gradually spiraling in at exactly the rate that general relativity predicts because of the loss of their binding energy in the form of gravitational waves. But the direct observation of these waves, not from Hulson-Taylor, but some other binary coalescence event, was observed in September 2015, as I mentioned earlier. These, what you see now, are how the gravitational wave strain observed in these interferometric detector was measured in the LIGO detector in Hanford and the Livingston detector, so LIGO detector in Livingston. And you notice how consistent these two signals are. Of course, we have actually moved in time one of these signals and overlapped it with the other one in the other detector in this right panel. We have also flipped the phase by pi to make them overlap. But this is all consistent because the two detectors are rotated with respect to each other by about 90 degrees, and they're also spatially separated by 3,000 kilometers, which allows for a maximum travel time of gravitational waves, which travel at the speed of light in vacuum, of plus minus 10 milliseconds. So here it turns out that we had to shift one signal relative to the other by 7 milliseconds. It arrived in Livingston that much earlier compared to Hanford, and that is consistent with the location of the source relative to the baseline that connects these two detectors. In the middle panel, we show the the templates and numerical relativity waveforms color coded that nicely explain these patterns, consistent with black holes with masses about 29 times the mass of sun and about 36 times the mass of sun. And if you subtract these theoretically modeled waveforms from this noisy data, and you have these strains remaining, which are quite consistent with noise. In fact, this kind of an event would have been produced by noise, as we saw, in about 1 in 200,000 years. So that's a very strong vindication that these are real signals. And this particular event happened about 1.2 billion years ago. In other words, the merger happened in a galaxy far, far away. How far away? About 1.2 billion light years away. And if you want to read more about this discovery, you can refer to this paper by the LIGO and Virgo collaboration published in 2016. So as I told you, we have to learn a little bit, or maybe revisit, because you must have been exposed to tensors in the past. But yeah, so we begin with electromagnetism to refresh some of our memory about them. A straightforward example of a tensor is a vector, and because space and time are intricately linked in special relativity, we will talk about vectors and tensors as space-time objects. So a good example of a four vector is the electromagnetic four vector, bold-faced A, whose time component is the electromagnetic potential. In the past, that used to be called the scalar potential, and its space component AK, where K takes spatial indices x, y, z, or 1, 2, 3, also denoted with and a vector on top. Okay, the spatial object is the 3 vector potential. But you will find that as these lectures progress, that the scalar potential and the vector, 3 vector potential, are really parts of a single object, namely this 4-dimensional electromagnetic 4 vector A. And the electromagnetic, or the Maxwell field tensor, is an object which has in matrix form, it's a 4 by 4 matrix. So it's a rank 2 matrix where mu and nu are space-time indices. They both span over all of those space-time index values, so time, x, y, and z. By the way, instead of x, y, z, you can use some other coordinate system like r, theta, phi as well for the spatial coordinates. And f mu nu is described in terms of this combination of first derivatives of the vector potential, this 4 vector potential, with respect to the something that is related to the space-time coordinates, okay, these x mu's and x nu's. This is antisymmetric under the interchange of mu and nu. So this can be written in this compact form, where this square bracket denotes antisymmetrization over its argument, which are these 2 indices mu and nu. The factor of 2 here is conventional. So this is exactly how this square bracketed quantity is defined in terms of these first derivatives. So f mu nu is antisymmetric under the interchange of mu and nu. And you can write the Maxwell's equations in this very compact form as a single space-time derivative of f mu nu being proportional to the 4 current vector, another space-time vector, j mu. Here mu 0 is the permeability of space, right? So that's all there is to the Maxwell's equations. But yes, I'm sure you're more familiar perhaps with the explicit form of these equations, which are 4 in number, like Gauss law, Faraday's law, Ampere's law, and so on. So how do you get those equations from here? So I think I'm going to go through that in the next few slides, because that helps us become to be at ease with tensors and their components in certain coordinate systems. So first of all, the electric and magnetic 3 vectors. So these are vectors with only spatial components, right? How do we get them from the 4 vector that we defined earlier, the electromagnetic 4 vector A? We do it exactly in this form that you are again very familiar with. Like you already know that the magnetic field is nothing but the curl of the, in this case, the 3 vector, the spatial part of the electromagnetic 4 vector, right? What about the field tensor? The f mu nu, the components of the field tensor, can be expressed in terms of the spatial components of the electric and magnetic vectors as follows. In this case, I have deliberately inserted back the factors of c, the speed of light. So, this is exactly how f mu nu is. And you will notice here that this is explicitly or manifestly antisymmetric, right. So, f 0 1 is exactly f 10 times -1, okay, and the diagonal components are zeros as expected of antisymmetric matrices. Now, you can take this as an assignment, a very easy one, where if you take the first derivative of f mu nu, you will of course get derivatives of these e's, and you can reproduce the 4 Maxwell's equations. Okay. So, notice that at some point you will have to bring up this factor of epsilon naught, which appears in Gauss's law, and that is the permittivity of free space. How does that appear? Actually, it is not very difficult. It is related to the fact that c, the speed of light in vacuum, is defined in terms of mu naught, which you already met earlier in that compact form of the Maxwell's equation, and permittivity of space epsilon naught. So, that is how you can bring out this factor of epsilon naught. But a little hint on that exercise I just gave you on how you can extract those 4 Maxwell's equations. So, let us start with this compact form, right. You will notice that this really is 4 equations, and that is because what is implicit is an application of a convention we call the Einstein's summation convention, where repeated up and down indices, okay, indices in the superscript and subscript, are taken to be summed over all of the values they are permitted to cover. So, because I am using here a repeated index nu, which is Greek letter, it means that this summation over nu is over all space-time indices 0, 1, 2, 3. An example of that is that, okay, consider the case where mu is 0. So, nu is summed over. So, nu is a dummy index, as we call it, on the left hand side. It does not appear on the right hand side. Even if it did appear on the right hand side, it would be again summed over. Okay. Generally, it is a good practice not to use multiple the same letter for multiple summed indices in the same equation on the right or left side. Mu is the free index. So, there is this occurrence of mu as an index on the 4 current, and it is not summed over in the right hand side, which means that you should verify the existence of that free index mu also on the left hand side, and indeed it is. It is one of the indices on the field tensor components. So, then let us choose the special case where mu is 0, the time component. Okay. So, nu is still summed over, which means that the single derivative, space-time derivative of f 0 summed over nu really should be written out like this, where in the first term on the right hand side nu takes the value 0, the time index, then the second one nu in both places is 1 or the x coordinate. In the third term in both places nu is equal to 2, so that is the y coordinate, and then finally nu is equal to 3, the z coordinate. So, this is what the Einstein summation convention is. So, this is an illustration of it. But we know what these f's are because we showed that on the previous slide, and f 0 0 was 0. So, that does not contribute anymore, but f 0 1, f 0 2, f 0 3, those are just the x, y, z components of the electric field, okay, but with a factor of 1 over c, which now is common. So, is taken out, and c is a constant. So, the derivative, this spatial derivatives do not act on c, they just act on the electric field components. And when you write them out, you realize this is all but the divergence, right. So, this is the 3 divergence of the 3 vector that we call the electric field multiplied with 1 over c. But then the Maxwell's equations would have us believe that this should just be mu naught times j 0, because I have set mu equal to 0 on both sides. So, this should be mu 0 j 0, but j 0 by definition is just c times rho, okay, the charge density. You will meet rho later where I will use it as energy density, but that is why I will clarify here. Rho stands for charge density, and because c is 1 divided by mu naught times epsilon naught, that is why Gauss's law really is just divergence of E up to this factor of c, time equal to rho divided by epsilon naught. So, yeah, you may have to insert a factor of c here and there in the Maxwell's equation I gave you earlier. So, that is a test for you. And another familiar fact of electromagnetism is that it entertains a wave equation. That is very easy to see from Maxwell's equations, because all you do is you pull that up and then apply the definition of f mu nu in terms of the antisymmetrized derivative of the electromagnetic potential A, right, and that is then set equal to mu naught times j mu. Here, by the way, the naught on mu is not a time index. Okay, it is just naught is integral part of mu, and historically we have termed mu naught as the permeability of space. So, so that's just a disclaimer here. Fine. So this is actually almost it almost has the form of a wave equation, and indeed so. But before I come to that, I will point out that the electric and magnetic field expressions in terms of derivatives of A you can use to verify that those equations are invariant under this coordinate transformation, under this star transformation known as the gauge transformation, where you reset A mu to this new quantity A mu prime, which is the old A mu plus this derivative of a scalar lambda. Okay, lambda can be space-time dependent, but it is the derivative of the scalar with respect to your space-time coordinates. So, so this kind of a transformation will leave the electric and magnetic, so-called physical fields unchanged. Similar gauge transformations exist in the theory of gravity as well. So, and you will see that especially in discussion of the linearized approximation of Einstein's equations, which I will not cover, but one of my colleagues will. So, watch out for that. But another exercise you should pursue is take this equation, Maxwell's equations, but written in terms of the A mu's, and show that you can recast that in this form, where this square with this power 2 is just the D'Alembertian operator. It can be expanded in terms of pure Laplacian, which is contraction over spatial indices alone, and this double derivative with respect to time up to a factor of c square. And when this is set equal to 0, that is in vacuum, where there are no charge densities or currents, then indeed you get a wave equation, and by solving it you can find the wave solution. So, electromagnetic waves oscillating and propagating in vacuum without the need for any material medium to sustain them. So, now I am going to slowly transit to introduce objects more general than what you just saw in electromagnetism, but as a transition example I will persist with vectors. So, recall that any space-time vector can be expanded in terms of what in the past we used to call unit vectors. I will call them space-time basis vectors, because there are 4 dimensions. We will use 4 basis vectors, E0, E1, E2, E3. The reason these 0, 1, 2, 3 are now encouched in this parenthesis is because I do not want you to think of E0 with the 0 being a component, namely the time component of this basis vector. No, that is not the case. Rather, there are 4 of these basis vectors. Okay, E0 itself with the parenthesis around the 0 is a vector in space time, but you can find coordinate system where this E0 basis vector is aligned with your time coordinate. Okay, in that case, only the time component of E0 will be 1, because it is also a unit vector, and the other components, the x, y, z components, will all be zeros. Similarly, E1 basis vector, you may choose your coordinate system to align the x axis with this basis vector, or yeah. So, and in that case only the x component will be 1, the time and y and z components of E1 will all be zeros, and similarly for E2 and E3. So, if these are your basis vectors, then any space-time vector A, which was introduced as the 4 vector potential, but it can actually be any general vector. It could be the space-time separation, okay, between 2 events, right. so any such vector can be resolved in terms of these 4 basis vectors. So, A can be written as A0 times E0 vector plus A1 times E1 vector, and so on and so forth. In a compact notation, you can use the Einstein summation convention to express this in this fashion, where it is just A mu times E mu with mu summed over 0, 1, 2, 3. Okay. This is exactly what A mu times E mu means, this expansion over 0, 1, 2, 3. So, we will also variously call this as A mu E mu contracted over mu or summed over mu. In a different inertial frame, okay, let us say a frame that is boosted with respect to this first one, the components of your vector can change. Indeed, you know that the electric field, which is not a space-time vector, right? I mean, our old baggage, if you are carrying it with us still, then we call the electric field vector as a 3 vector. It's a spatial vector, but really it has problems, because there's no way you can just deal with it under Lorentz transformation and figure out how its components will change. The right way to do that, unless of course you go in a very circuitous fashion, but the easiest and the straightforward way to do that is to realize that the electric field vector, that 3 vector, are really extracted by differentiating this 4 vector A. So it is important to know how the components of this 4 vector A transform under coordinate transformation, some general coordinate transformation, but specifically that is a Lorentz transformation that relate one inertial frame to another, where the two have some constant relative velocity, right. But a boost or a Lorentz, a Lorentz transformation is not limited to just a boost, right. You can also have rotations, but that is also fine, because the Lorentz transformation in general will still allow us to connect the components of A in one inertial frame with the components of the same vector A in a different inertial frame. Okay. Namely, so if the other inertial frame is labeled by the primes, the prime coordinates, like x mu primes, so explicitly there would be t prime, x prime, y prime, z prime, right. Then A can be expanded in this fashion over the corresponding basis vectors, E0 1 prime, sorry, E0 prime, E1 prime, E2 prime, and E3 prime. Since we are talking about Lorentz transformations, it helps to recall the Lorentz matrix, and in this case I am going to just limit myself to simple boost along the positive x direction. So, for that situation, the components of the Lorentz matrix, so lambda nu prime mu, where mu denotes the coordinates of the, let us say, the classroom frame or the non-moving frame, also just the S frame, and nu prime denote the components of the moving frame. Okay, so could be your friend in a car moving with respect to you in the classroom with a relative velocity of v in the positive x direction. So then this v is the magnitude of that velocity, and gamma, the Lorentz factor, is related to v in this fashion. It is 1 divided by square root of 1 minus v squared over c square, and c is set to 1 here. Similarly here, wherever you see v, you should be replacing v with v over c if you were to reinsert the c's. So what happens under Lorentz transformation to the components of the space-time vectors, right? That was what I was describing on the previous slide, but here we will give you the explicit relation. So if this is my Lorentz transformation, which is just a boost in the x direction, then these are the components of the v's expressed in terms of the coordinate derivatives dx by dt, and incidentally the time component of this velocity is then just dt by dt, which is 1. So that is trivial, but I mention it here because there will be some interesting situations that will come up later. So the components of our good old A vector, that 4-dimensional vector, now transform under lambda nu prime mu, or the Lorentz transformation, like this. Here again there is a summation convention over mu. So and you can go back and verify that this tells you that if A mu happen to be some not necessarily the electromagnetic 4 vector, but some other vector. For example, just your 4 velocity vector, right, and you are sitting in the room. So, in that case your spatial coordinates are not changing with time, right. So, the x, y, z components will all be zeros, only the time component will be non-zero, but you will find that this Lorentz transformation is going to mix up those components. So, that from a moving frame your 4 velocity vector will now assume non-zero spatial components as well, and that makes sense because with respect to a car, you in the classroom are actually moving away in the opposite direction, the negative x direction, right. So, the Lorentz transformations of course have that correct Galilean limit. What is somewhat counterintuitive is that this transformation mixes up the time and space components. So, I am assuming you are familiar with special relativity. So, I am not going to go into resolving the paradoxes that are well known there, but you can use this transformation to resolve them. So, this will be one component into resolving them. Of course, there are some conceptual ingredients that you will have to apply as well for resolving some of those paradoxes. But this tells us a couple of things. First of all, the vector, or in general a tensor, a space-time tensor, is unchanging. Okay, that is not what changes. What changes under coordinate transformations are its components. Okay, so, the a mu's will change. A itself is fixed, and this realization also helps us in working out how the basis vectors are going to be related to each other. The basis vectors of the prime frame and the unprimed frame. So, S prime and S under any coordinate transformation, but specifically here in this Lorentz boost, right. So, how do you figure that out? You expand A first in terms of your basis vectors natural to the S frame or the unprimed frame or the unmoving frame, and then secondly in terms of the prime frame or the moving frame, right. But you know how A mu and A alpha prime are related, and that is equation 1. All you have to do is just replace your nu primes in 2 places with alpha primes. Again, that is just simple index recognition and gymnastics, right. Once you do that, then you apply the Lorentz transformation from 1 onto the components of the A. So, you replace the A alpha prime in terms of A mu's, and then once again you take this right hand side term to the left hand side and replace and realize that A mu is common to 2 of the terms, which means you can extract it out of this parenthesis, leaving you with an expression that connects your primed basis vector to the unprimed basis vector. Okay. But this equation, the fact that this has to be 0, must be respected regardless of what your choice is for A mu, which means that the parenthetic expression should identically vanish, and that tells us that the non-moving frames basis vectors can be expanded in terms of the prime frames basis vectors through this Lorentz matrix. And you notice that if you compare the transformation 2 with transformation 1, you will notice that they are different. Okay? And that is because the primed components of the vector are appearing on the left hand side in equation 1, whereas the unprimed basis vectors are appearing on the left hand side of equation 2. So, this is why sometimes we say that these vector components are contravariant, meaning they transform contrarily to how the basis vectors transform, although that language is actually deceptive. This is not transforming the basis vectors, this is in fact relating the basis vectors of the 2 frames. Okay? And remember, the vectors themselves are not transforming, it is just that components are related in this fashion. So, oftentimes we therefore just call these as components of vectors, but sometimes you will come across this old terminology where these components are called contravariant components. Actually, the nomenclature can be even worse. In some old literature, you will find vectors whose components have these indices in the superscript being termed as contravariant vectors. There is no such thing. Okay? So, those are just vectors. Is there components at best that may transform contravariantly or contrarily to how the basis vectors are related. That is one example of a tensor. namely 4 vector. Are there other examples? Yes. A second example which you have met in some form in special relativity is the metric. Okay, what you have dealt with is the Minkowski metric, which is 4 space-time dimension. It's a rank 2 metric. So it has in components, it has components g mu nu. Often you may have actually seen this in the form of eta mu nu. That's the Minkowski. Those are the Minkowski metric components. Mu and nu take 4 values each. So this is a 4 by 4 matrix. But what really is a metric? Okay, so let me actually go on. Oh, yeah. So let me tell you a little bit about the Minkowski metric and then come back to the definition of a metric. But actually, so the metric, a general metric, not just the Minkowski metric, is a map that acts on 2 4 vectors, for example, A and B, to produce a scalar. All right. So that's the basic definition of a metric. And this scalar, by definition, is invariant under transformation. So in special relativity, this would be, for example, a Lorentz transformation. So in that sense, it is an extension of the concept of an inner product between 2 vectors. So G is a map that takes 2 of these 4 vectors as its arguments, and in that sense, it is like the inner product, which also takes A and B as its arguments and produces a quantity which is a scalar. And the way you are writing the scalar here is again in terms of 2 contractions. So now comes the first complication in the application of the Einstein summation convention, namely that we are now applying it twice, over the index mu once and over the index nu a second time. All right. So, and we will expand this in an example very soon, but this quantity is invariant under Lorentz transformation, and that is because you can show that the same lambda factors that are involved in transforming the A's and the B's to the prime frame components will actually transform G mu nu in a way that will take it to the correct components G mu prime nu prime in the prime frame, so that the net quantity does not change its value at any given point in space and time. So as an application, yes, let us go to that flat space time example. So eta mu nu, and again Cartesian coordinates, so that all of these are diagonal. So this these are the components of the flat space time metric, for example in your S frame. Now G acting on AB is this inner product. So what's an example of the metric eta acting on 2 vectors? What would you consider as your 2 vectors? An easy example is where A is the space-time separation vector, call it delta x, okay, but 4 vector. B can be said to be the same thing, delta x. So if you do that, then eta acting on delta x and delta x is, by this definition of the map, just eta mu nu contracted twice with delta x mu and then delta x nu, right. So there are 2 indices that are contracted. So if you expand this, then you get eta 0 0 delta x 0 delta x 0, but eta 0 0 is simply -1 and delta x 0 times itself is the square of it. So the first term is negative delta x 0 squared. Delta x 0 is simply delta t squared, that is the time separation of 2 space-time events. The second term here would be eta 0 1 delta x 0 delta x 1, but eta 0 1 in this coordinate system is 0. So therefore it does not contribute to this expansion, this sum. Then you have eta 0 2, similarly that is 0, then eta 0 3 is also 0, then eta 1 0 is 0, so no contribution to the sum. So the next non-trivial contribution comes from eta 1 1 multiplied with delta x 1 delta x 1. So delta x 1 is just the x coordinate, that's written here. So delta x 1 square, and eta 1 1 is simply positive 1, so that is the positive 1. And you can work out the rest. So you get delta plus delta y square and then plus delta z square. So this is the invariant line element, right. This is the interval, space-time interval that is unchanged under Lorentz transformation. And so the metric is indeed mapping the separation vector between 2 space-time events into that invariant. Okay, this is a flat spacetime example, but metric by definition does that even in non-flat situations. So, this realization can be utilized to understand another interesting property of the metric, and we do that as follows. We again revisit that basic definition of the metric as this map and the inner product, but now you know that A dot B, the inner product, can be expressed differently as follows. You replace A with its expansion over the unprimed basis vectors and do the same thing for B. Okay. Yeah, it is important that you don't mix up the coordinate system. Okay. If you do that, then you will have to be careful about this map, because this map, if you want to express this map in a coordinate system, you have to be consistent about that coordinate system. You cannot mix up coordinate systems. In fact, that is one reason paradoxes appear. So, go back and check with special relativity and try to avoid that. So, that is why here we use the same unprimed coordinate system in both cases, right. So, then but A mu and B nu, there are 4 of these in each of these cases, and but they are just scalars. So, you can take them out together, leaving you with the inner product acting on the 2 basis vectors E mu and E nu. Okay. But this inner product is indeed what this map is, G mu nu. So, this is how we are defining G mu nu. So, the components of the map G are nothing but G mu nu's, which are just the inner product of these basis vectors. So, this is something that closes this circle here. You may complain that well, you have G mu nu as the third factor in this equation 3, but it was the first factor in equation 1. Yes, they commute, that is because these are just numbers at any given space-time point. But this allows us to introduce another notation, namely that you realize that G mu nu is contracted over index nu with the components of the vector B. So, this in a stroke of simplification of notation, you can combine these two to define a new quantity B mu with mu downstairs now, or a subscript. Okay. So, that is a definition, but it is a convenient one. So, in the process, what we have really done is we have seen that equation 3 tells us that G acting on one vector, okay, with the other argument unspecified, really has components, okay, which are B mu's with index down. But this cautions us that we should not mix up the components, because B with index up is not the same as B with index down, because B with index down really has an extra factor, or actually a summation with G mu nu, and the G mu nu's here may not be trivial, they may not all be 1. In fact, even in flat spacetime, you know that eta 0 0, okay, where mu is 0 and nu is 0, is -1. So, you cannot mix these up. Even in flat spacetime, but in curvilinear coordinates, you have to be careful, because eta r, for example, can be r square. So, B with index up, like BR up, is not the same as with BR down. Okay? And in curved spacetime, you have to be all the more careful. What I did on the last slide with B with mu indexed down actually hints at another quantity. So, we have introduced 2 types of tensors. The first was a vector, the second was a metric tensor. Now, I am going to introduce something called the dual vector. Okay. Eventually, these are useful to define another kind of construct, namely a 1 form, or in general an n form. But for now, I am just going to stick to dual vectors in the following sense. So, this actually answers a question, namely that can there be a map that takes a vector to a scalar? Well, how did we come up with this question? We did so by realizing that a metric takes 2 vectors to a scalar. So, can there be a different type of map that just acts on 1 vector? You sort of saw that here, where we are using the metric to act on a single vector, but that did not produce a scalar. See, that is the catch. Here, we want to produce a scalar. So, this object has to be different from a metric. So, what is it? This is what is called a dual vector, and notationally we indicated with a bold-faced letter with a tilde on top. Okay. In this case, that letter is being used as p, but it could be something different eventually. But the question is, p tilde acting on a vector A, can that produce a scalar quantity? Scalar meaning unchanging under coordinate transformations, and in special relativity, for example, Lorentz transformation. So, how do you do that? One way is to expand A in terms of the basis vectors E mu's, and then say that the maps, again borrowing a leaf from our discussion of the metric, P should act on a vector. So, A mu's are just scalars, so they can be taken out of this action. So, then P acting on E mu better be an object that is contracted with A mu, because that is what we learned on the previous slide as something that can produce a scalar, an invariant under Lorentz transformation in special relativity, right. So, let us call this quantity which has this free index mu as P mu, and so now mu always was contracted. Okay. So, there is Einstein summation convention again in action here, but this contracted quantity is a scalar. So, A mu times P mu is summed over mu going from 0 through 3. So, this is then a dual vector. Okay. So, P is a dual vector in the sense that it acts on a vector to produce a scalar. Now, so in that sense, on the previous page when we acted G on B, that was that produced a quantity B mu, which were actually components like P mu of a dual vector. Okay. So, a dual vector is called as a 0, 1 tensor in the sense that it acts on a vector to produce a scalar. A metric is a 0, 2 tensor. So, this is again a different notation. The 2 here indicates that it acts on 2 vectors to produce a scalar. Okay. So, when will you be able to convert the 0 to a 1? If you want to do that, you will produce a different map, not a metric. So, 1, 2 tensor is an object that acts on 2 vectors and a dual vector to produce a scalar. All right. So, in that sense, a vector is a 1, 0 tensor. Okay, 1 on top, 0 down here. So, vector is a 1, 0 tensor that acts on a dual vector to produce a scalar. So, that would then be the opposite of this action, but producing the same result, the same scalar. But to understand that, it helps to introduce now the basis vectors in terms of which we can expand any dual vector. Okay, so, these are analogous to the E0, E1, E2, E3 we met earlier, right. So, we now call these basis dual vectors as omegas. So, that means that a general dual vector P tilde can be expanded in terms of these omegas through these components P betas. Specifically, this is the interesting thing, P acting on the basis vector means P beta times omega beta acting on a basis vector, but you know that P acting on the basis vector should really produce this P mu, the component of P, which means omega beta acting on E mu should produce a Kronecker delta, namely delta beta mu, because that contracted with P beta will just be P mu. Hence, a vector is a map that takes a dual vector to a scalar. Okay, so, A acting on P, the dual vector, is the same as A, the vector acting on P mu contracted with omega tilde mu, but P mu being a scalar can be taken out. Okay, here I do not mean scalar in the form of an invariant really, but just a scalar function. Okay, so, that can be taken out. And A then acts on omega tilde mu, and you get P mu times A mu. All right. So, this is consistent with equation 1. Both are exactly the same quantities, and because these are numbers at any given space time point, they commute. So, like this vector, namely a 1, 0 tensor, in general you can have mn tensors. So, an mn tensor is a map that acts on m dual vectors and n vectors to produce an invariant. Some examples so I am going to wrap up in a couple of slides this first lecture, but I will give you some examples of vectors and dual vectors. The space-time interval you already know is a nice example of a vector. Its components are these delta x0 or delta t, delta x1 or delta x, and so on and so forth. A 4 velocity vector is again from special relativity, but again 4 velocity is applicable even if you are moving in curved space time, because any curved space time you will realize can be populated with local inertial frames, all right. And so locally this 4 velocity vectors will tell you exactly how you are moving, even though at the next space time point that 4 velocity vector may change, meaning you may accelerate because of the curvature of space time, or therefore because of gravity. So 4 velocity vector v is just the derivative of x with respect to the proper time tau that the moving object is carrying with you. So this is the time you're measuring with your clock, and so the components of this are just dx0 by d tau, dx1 by d tau, and so on and so forth. And these are then for the components of this 4 velocity vector. You can go on to construct many interesting vectors from this. In fact, the 4 momentum vector is one such, and that is just p, which is m times v, where m is the rest mass of a particle whose 4 momentum you want to describe. Here p is a 4 vector, so don't get confused with p tilde, the dual vector you came across on the last page. Okay, the tilde there in fact was useful to resolve that confusion. Okay, so that is different, and that's because ultimately we have only 26 letters in the English alphabet. We have many more quantities in physics, but that's not something you're not already familiar with. So dual vectors examples: gradient of a scalar field phi. Yes, that is not a vector. I know in Euclidean geometry many of us are used to thinking of gradient as a vector, but this 4-dimensional object is truly the dual of a vector. Okay, it is not a vector because it does not, its components don't transform like the components of a 4 vector, and that is the key to understanding that this is not a vector. In fact, the components of d tilde phi, this gradient of a scalar field, are d phi by dx0 and so on and so forth. Notice that these space time coordinates are appearing in the denominator here, as opposed to the components of a vector, the 4 velocity vector, which were appearing in the numerator. That gives away the fact that under a Lorentz transformation, it is the inverse of the Lorentz matrix that will be used to transform these components from the unprimed frame to the primed frame. So the components of a dual vector actually transform differently than the components of vector, but they therefore transform similarly to the basis vector, which is the reason why, again, in old language the components of a dual vector were described to transform covariantly. Okay, you already heard me introduce the term contravariant in the past in the context of vectors. Dual vectors, again, in abuse of sorts, were termed as covariant vectors, but again that is not correct language. So we will limit ourselves to just dual vectors and their components, which transform differently from the components of a vector. Another example of a dual vector is the vector normal to the surface. The surface is described by some function f as a function of the space-time coordinates, right? And the gradient of that function is really the normal at any given space-time point. So the normal by extension is again not a vector, something that you may or may not have realized in the past. So this again really is a dual vector problem. Think of a few more dual vectors and vectors. I'm going to end with these couple of questions. Figure out how the basis dual vectors omega tilde beta transform under a Lorentz transformation. The idea is going to be very similar, something you use to figure out the basis vector transformation, right, when we talked about vectors. So try to use something like that in understanding how you are going to relate omega tilde alpha prime to omega tilde beta through the Lorentz transformation matrix, lambda alpha prime beta. Okay. Second question is energy a scalar under Lorentz transformation? If not, then what exactly is it? Okay, trivia here is that the electric potential A0 is also not a scalar, right? And that is because that Lorentz transformation tells us that A0 really transforms as the time component of a 4 vector, okay, A. And so that doesn't mean, well, so maybe use that as a hint to figure out what exactly the energy E is of a particle under Lorentz transformation. Okay, with that we end the first lecture. Thank you.